Let us now look at another problem which also deals with the kinematics equations. So a particle is moving along a straight line with the acceleration a is equal to 12t minus 3t to the power 0.5, where t is in seconds. We're asked to determine the velocity and the position of the particle as a function of time, and we're given that when t is equal to 0, that's the base reference, v is equal to 0, and s is equal to 15 feet. So again, the very first step is to identify the coordinate system we're going to use. Since we're dealing with a rectilinear motion, which is mentioned in the given by straight line, so we know that we're working in one-dimensional space. So again, there's no confusion in terms of which coordinate system to use. We can move to the next step. And so we need to write down what we know. We have an expression for the acceleration in terms of time, and we're given initial conditions. At t equals to 0, we have v and s. And we can also remember the fundamental equations we've seen. We know that a is equal to dv over dt, and v is equal to ds over dt. Remember, these are the two independent fundamental equations we have, since the third equation we've seen, which is independent of time, was actually derived from these two equations. So it's kind of useless to add the third equation into the list. Now, since we have an equation, an expression for a as a function of time, and we know a relationship between a and v, including time, we can easily find v by making use of that equation. So we know that a is equal to dv over dt, and so dv is equal to a dt. Then we can integrate both sides, the left-hand side from v0 to v, and the right-hand side from t0 to t. And then integrating the left-hand side would give us v minus v0, while the right-hand side, we actually need to input the expression of acceleration as a function of time in order to integrate it. So I have 12t minus 3t to the power 0.5, and integrating that, we get 12t squared over 2 minus 3t to the power 1.5 over 1.5 from t0 to t. Now remember, t0 is equal to 0 since it's the reference or the base for the time, and so we can get rid of this term, and so we'll end up with v minus v0 is equal to ct squared minus 2t to the power 1.5. Again, since v0 is equal to 0 from the initial condition, we'll get an expression for v, which is equal to 6t squared minus 2t to the power 1.5. Now that's great, we solved half of the problem. We were asked to find an expression for v and the position. We found the expression for v. Now how can we find the expression for the position? Well, it's also easy. We need to remember that v is equal to ds over dt. And so if we have an expression for v, we can write that ds is equal to v dt, then simply integrate. Now performing the integration, one gets s minus s0 is equal to the integral of the expression of v dt from t0 to t. And so we end up with an expression for s as a function of time. Now, this example is particularly interesting since it actually shows us how we can find expressions for the velocity and the position given the acceleration by simply using the fundamental equations. So you can simply integrate the fundamental equations to move from the acceleration to the velocity and then to the position. Now, similarly, you can go backwards. So assume you were given the position as a function of time, you could derive this expression and get the velocity, then derive that again and get the acceleration. So it's very important to keep that in mind when solving problems.